Welcome back to Engineering Foundations. Today we're digging into the invisible forces that hold our world together, literally. If you've ever walked past a massive concrete retaining wall alongside a highway and wondered why it doesn't just topple over under the weight of all that dirt, you're thinking about lateral earth pressure. To make sense of this, engineers looked to William Rankine, a 19th century polymath who gave us the mathematical keys to predict how soil behaves when it's pushed to its limit. At the heart of Rankine's theory are two primary coefficients, Ka and Kp. These aren't just random variables, they represent a ratio of horizontal stress to vertical stress. Essentially, they tell us how much push the soil exerts sideways based on the weight of the soil pressing down. Whether a wall stays upright or collapses depends entirely on which direction the structure is moving and how the internal friction of the soil particles, defined by the angle phi, reacts to that movement. First, let's talk about the active state, or Ka. Imagine the retaining wall leaning slightly away from the dirt it's holding back. As the wall moves out, the soil stretches and relaxes, reaching a minimum pressure point just before it shears and slides downward. Because the soil is helping itself stay up through internal friction, the pressure on the wall is relatively low. In the math, K sub A is calculated as 1 minus sine phi over 1 plus sine phi, which usually results in a decimal like 0.3. It's the baseline force most designers have to account for. On the flip side, we have the passive state, or Kp. This is a completely different animal. Imagine a bridge abutment being shoved into an embankment. Now, instead of the soil relaxing, it's being compressed. You are fighting against every grain of sand and clay, forcing the earth to heave upward. Because the soil is resisting your movement with everything it's got, the pressure skyrockets. The formula flips to 1 plus sine phi over 1 minus sine phi, meaning Kp is the mathematical inverse of Ka. If Ka is 0.33, Kp is a massive 3.0. However, there is a catch that often trips up junior engineers: the strain, or the amount of movement required. Reaching the active state is easy. It only takes a tiny fraction of an inch of movement for the soil to fail into the wall. But to reach that full passive resistance, you have to shove that wall significantly further into the ground. If you rely on Kp to stabilize a structure, but the wall doesn't move enough to engage it, your calculations might be dangerously optimistic. Understanding these coefficients is the difference between a highway that lasts a century and a landslide that makes the evening news. Rankine's beauty lies in his simplicity. By assuming the wall is smooth and the ground is level, he gave us a clear, elegant way to visualize the struggle between gravity and friction. So the next time you see a retaining wall, remember, it's locked in a silent, mathematical tug-of-war between the active push of the earth and the passive resistance of the foundation.